Hey, welcome, guys. We're gonna wait for 5 minutes, wait for people to roll in, basically. Um, what I'll do is I'll put on some lofi music in that time. Grab your bottles, and then at 7:05 we'll jump right into the workshop. See you then. Hey, hey everybody. I hope you guys can hear me okay. It's 7:05, so we'll get started. I'm gonna get Liam on here, and he's just gonna basically dive right into the workshop. So without any delay, um, bring Liam up on screen. All right, good luck.
All right. Hi, everyone. Hopefully you can see me and hear me okay. My name is Liam, and I'll be talking to you today about linear regression and doing an implementation through gradient descent, which is a particular technique that's found in a lot more complex machine learning techniques, and it's pretty convenient and helpful to understand that before diving into something like a neural network. If anyone, oh yeah, there we go. There's the slide deck. So yeah, I'll start going into that now then. So again, like I said, my name is Liam. I'm studying math and CS at the University of Arizona. I do undergrad research both at UA and University of Utah, and I'm also a software engineering intern at a startup called Toolchain Labs. So briefly going over the agenda for today, we'll start off with going over what a regression is, comparing simple and multiple regressions, some pretty simple math, just of regressions and gradient descent, and then we'll implement it in Python together. Also, feel free to put any questions in the comments thing. I can see that if you guys have any immediate questions. So what is regression? Fundamentally, it's just the process of fitting a particular curve to a data where you have an input and an output, or just two variables in general in this case. We want to find a function that represents how well our curve predicts that data, which is called the goodness of fit function. Generally speaking, the more complex your curve is, you'll end up with a better model fit overall. But you also end up with the problem of having something that's fairly complicated to implement. So ultimately, you want to find a balance of something that's fairly trivial to implement, fairly straightforward to implement, but still is a good representation of your data. Just as an example, I have this hypothetical set of height in feet versus weight in pounds data. So just in a more tabular representation, we have these two arrays here. So consider this just like pseudocode. So we have an arbitrary model that takes in our weight and our height, and we predict for a given height what their weight will be. This is a pretty straightforward, this first one right here, as we already have this particular data point. So if assuming our model works well, we'll have a perfect output where we have 5.5 linked to 112 in our data. That's this point right here. And we have, again, our model predicting a perfect output. If we just had a line going across here, that could be our hypothetical model. We can also predict for a point that we don't have an exact data. As you can see, we don't have the height 6.4, but we do have, but we can make a prediction for that height based upon extrapolating from this data. That generally speaking, a regression is just a way to do this. So our model here would just be some object that could regress. But hopefully that gets the gist of what exactly a regression is across. So in that past example, we had a singular input to a singular output. We call that a simple regression. If we have multiple inputs to a singular output, we call that a multiple regression. Just for the sake of extending gradient descent and understanding it first before extending it to things, this talk will be focusing on simple regression. So just one input to one output. So if you look up an implementation for linear regression, let's try that. There we go. That's a bit better. We'll see that a particular technique called least squares or ordinary least squares is usually used. There are a variety of reasons for this, but generally speaking, it's not super important to understand ordinary least squares or that computation, because no deep learning method whatsoever, which is generally speaking the state of the art for machine learning algorithms, uses that, whereas gradient descent is extremely extensible and can be used in a wide variety of applications. So our implementation will be through a gradient descent approach rather than ordinary least squares. So first, before going over more specifically the implementation of a linear regression using gradient descent, it's quite fruitful to understand what gradient descent actually is. The intuition behind the process is pretty simple and very trivial. Basically, you have something, you make a small change, you see how good or bad that change is, and you make another change in that correct direction. So as an example, you can make a change. If that change approaches a minimum of a cost function or a loss function, then you are going in the direction of improving your model. If you go and you end up with a reduction in an increase in cost, then you end up moving away from the ideal state for the model, and you'd make a prediction, or you'd make a change in the other way. So just kind of to get this idea across, I have this convenient little visualization here. So gradient is just another word for slope, essentially. So we have this tangent line that represents the slope at various points along this parabola. This parabola is representative of our loss function, which just is a measure of how good or bad our model is. So if our loss function is at a fairly high value, let's just say it's like up here. This y value is fairly high, it's 10 compared to, like, I don't know, it's -5, for example, which means our model is not very good. So ultimately, we want to approach this minimum of the loss function. Now, when we drag this line around, you can see that the slope of that line, if you just remember from your basic algebra class, the slope is just, how slanted this line is in the direction of its slant. If we, along here, we have a fairly high slope, fairly steep slope. So generally speaking, the worse our model gets, the higher our slope also gets. So when we find the point at which our slope is 0, we know that we're actually at the minimum of our cost function, which for this arbitrary cost function is just -5. Similarly, if our slope goes positive and grows larger and larger and larger, more steep in the other direction, we know, again, we are going away from the minimum. So again, that's kind of the principle that we want to use. So when our slope is negative, if we increase our slope, then we'll approach this 0. If our slope is positive and we decrease our slope, we also approach this 0. And again, the overall goal is to find the minimum of that loss function, which is just a measure of how good or bad our model is. Before we continue, does anybody have any questions about that, or do you want me to go back or explain any facet of that again? All right, cool. So no questions, so I'll keep going. So yeah, like I said, we want to make the small changes to improve how well our line fits the data, which is measured by our cost function. Again, we want to approach that minimum with the cost function. We know our line, again, this is remembering from that early algebra class, is of a form y equals mx plus b, where m is your slope and b is your y-intercept. So essentially we have these two variables right here. Our error is the difference between our predicted line and our actual data. So we can pull this up real quick, just as a measure or an example of this error. So if we take these sliders, we can change this y-intercept. These blue lines measure the error just between these 2 points. We can change our slope. And again, as we're trying to minimize error, we want those lines, on average, to be as small as possible. So just kind of eyeballing it, we can see, all right, that's looking pretty good. We can shrink this a little bit. And like, as an average, that's looking better, at least, than it was initially. If we do like that, you can see our blue line is huge, which means clearly this line is not fitting our data very well at all. We square the error for two reasons. Again, the error is just the distance between those two lines. The first of which is to make it positive, because if you have a line that perfectly is differentiated between points that are below and above it, you'll end up with a square error of 0, or sorry, a regular error of 0, a non-squared error of 0, which isn't a good thing because it's not accurately representing it. But the other reason is to give greater weight to the outliers when you're fitting the model. Again, like I've said 100,000 times, our goal is to minimize the average of those square errors. So to do this, again, we kind of go back to the actual gradient descent component. We differentiate with respect to two variables. In this case, again, it's that slope m and the y-intercept b. Plug in those current values for a proposed change in that line, and evaluate the change. The actual differentiation process I'll go over in the next slide. It's fairly trivial because we have a squared function, again, it's mean squared error, and this fancy little thing called power rule. But essentially it's just taking the derivative, and a derivative is just slope. We want to change those m and b values based upon the result of the plugged in derivative. We use an arbitrary constant k as essentially our learning rate. That's just a modifier of how much we change. If we consider again this tangent line, our slopes are fairly big here. So this k value is just our slope. So if we have like 3.4 and our minimum occurs here, if we just iterate by our value of our slope, we'll end up overshooting extremely quickly, which is not particularly efficient. So if we have our constant modifier here to change it, then we won't end up having the same likelihood of overshooting. We also progressively want to make our changes just smaller and smaller, because ideally we expect to get closer and closer to the minimum. So our updating functions are also fairly straightforward, given that intuition. So we have these changes in the values, and we have this modifier here that just, again, makes it smaller. So if we have a very, very large, or let's just say a super negative slope, we'll decrease it by our constant and subtract that negative slope. And a subtraction by a negative makes a positive, it's addition, so our slope will end up being increased. Similarly, if we have a positive slope, it's, again, we're subtracting by a positive number, which will decrease our slope. So again, going back to this, if we end up, let's just say we're at this position, and again, we want to approach that minimum. We have a negative slope here. We're adding a positive number, which a negative plus a positive is a more positive number, so we'll slowly approach that. In the second case, where we have a positive slope, we'll end up subtracting the value and decreasing it. Two important things to note. We do this again until we've gone to our minimum, which occurs when the slope is 0. And in this case, gradient descent will stop because we have no change here. So we're just adding or subtracting by 0. Or I guess subtracting by 0, because constant times 0 is 0. M minus 0 is still just m. So m equals m will obviously do nothing. So this looks very scary. But this is the math I was talking about to kind of ground it a little more. Basically, we have our cost function, which is, again, just summing all of the values between our predicted value for a given point and our actual value, and then squaring that difference. Then we just divide by the total number of points, and that's our mean squared error. Now, remember that we have an arbitrary, or a predicted line, which is also of the form mx plus b. So we have this substitution here, which is necessary for a calculus concept called the chain rule. So when we differentiate and we have a function that has other variables in here, specifically ones that relate back to this, just back to another function, it's important to differentiate also with respect to that. So we have our differential with respect to m and our differential with respect to b. We can resubstitute back here just for convenience, but these are our two functions that dictate how we're changing our slope with specific pertinence to linear regression. Again, this is our mean squared error derivatives with respect to slope and y-intercept for our regression line. I point out these things just because it's hard to take that math and turn it into code kind of on the fly. So I've written these out here before we actually do the implementation, just because, again, it's kind of scary and it's a big list comprehension. But essentially, this dm and db values are just the exact same ones that we have here. So this is our dm and our db. So just derivative with respect to slope, derivative with respect to y-intercept, and those derivatives are of our loss function, which is just mean squared error. And this yp is just our y prediction. It's the reason. So the reason we substitute in the end back here, like why would we do the substitution and just substitute right back? We make the substitution initially, again, like I said, for chain rule, but we don't necessarily need to keep it that way, especially when you're programming, you can store that in a temporary variable, and it just makes things a lot cleaner. So here we've stored the yp, the y prediction, in this here, and this is just all of our y predictions for the entire set of data. And again, we have our sum here. We have our x value for a given point, our y value, and our y prediction value for all of the x values, y values, and y prediction values in there. Does anybody have any questions about that? We can go over it again when we're actually implementing the model. Right, cool. So no questions. So keep going. So again, just kind of recapping everything. Our goal is to minimize the loss function, which in this case is mean squared error. This is the average difference between our prediction line and all of the data points we have in our whatever data set we're using. We can do so by approaching that point where the derivative, or just the rate of change of the function, is 0 for the parameters in our line, which is just m and b. So now it's time for the actual implementation. So I'll hop over here to our open notebook looking thing and start programming. So I'll give you guys a second. If you want to follow along, you can just pull up something in Vim or whatever text editor you like using. If you want to do it in Colab as well, obviously you're more than welcome. I'll just give you a second for that. Cool. All right, so first thing we're going to do is import a library convenient for visualization. So this is useful for visualizing your data initially, and later on it'll help us actually see our regression, which again is quite handy. Next thing, we want our actual data. I'm just going to copy these over from a file that I have. I can put them in the, that's the password. I don't know why I didn't copy. Send it into chat in a second, but for y values, our x values. These are just two arbitrary sets of data. You could think of them like the heights and weights or any half dozen of things. The only kind of important thing is that they're approximately linear. So let's just look at our data real quick. So as we can see, there's an approximately linear relationship between these two things. So each of these points is just a pair. So 1 and 2, it's right there. And again, it's roughly linear. So our next step will be to actually have the full gradient descent implementation. So we have our variables. We can just initialize them to 0. And our arbitrary k value. Again, this is just a modifier to make sure we're not overshooting. That's the y-intercept, and that's the slope. So comments. Yeah, I'll make the text a bit bigger. You edit. Where is the? No, there are notebook settings. Oop, that's not there. There we go, editor, and let's make that like, I don't know, 20 point. Should be a bit easier to see. Cool, let's keep going. So we want to have our array. This is just for saving the model essentially, but these will be all of our predicted values just for our x values. So we'll have our predicted line from these, but we want to store those predictions for each of these x values we have. So that's just for persistence. We have our n value, which is just the length of our data set, or the size of our data set. This loop right here is the bulk of the actual iterative component of gradient descent. Actually, let's make it 15. So this value is really small right now, and that's just because our data set is super trivial and super small. The bigger your data set is, the bigger the larger the number of iterations for gradient descent you need to have. So usually those two things. So things like, again, the number of variables you're optimizing for, the complexity of your data, and the complexity of your model are the kind of the three things that dictate how many iterations of gradient descent you need. So we'll have our y prediction array. And if you'll remember, so our y prediction is just a line that corresponds to the prediction for each of these points. Again, you can kind of extrapolate a line from any 2 points in this, but these will be our y predictions for every single one of these points for given our m and b values for our line. So those will be used for the actual iteration component. So again, like I said earlier, it's just kind of the temporary variable that we use for those derivative computations. So again, these are these two derivatives I had earlier. when I actually went over the differential component. So they look kind of complicated. They're long list comprehensions, and frankly, it's just because it's easier to have one math equation correspond to this one section. But if anyone has any questions about a particular facet of this, obviously feel free to ask. Pop that over. Actually, let's just rewrite that part. Change these to I just for clarity. So if we want to go back actually really quickly to actually multiple dimensions. Oh, so there's a question. All right, yeah. So how similar would the code be if we're trying to fit points with multiple dimensions? Size, weight, speed. So generally speaking, fairly similar. The overall structure is the same. The big difference is going to be that you have different predictors, right? Or with so that is still with one output. So again, I guess actually very, very similar then. So in this case, we have our singular x value here. So actually, let's roll back a little bit. So to kind of address this, we need to go back to the math component a little bit. We have kind of nice values here in that our in space, each of those points depends on fairly few things. In this case, it's literally just our x values. So you need to come up with, actually, let's think about this a little more. Yeah, I guess the bulk difference will just be in your derivative. So assuming with in that example, you'd have a completely different derivative function. You still have the yp here, but this substitution would be different, which means your chain rule computation for that value would be different. So you'd have differentials with respect to weight, size, and speed instead of just, if we're using the weight in my example, just weight here. But we'd still have it with respect to DNM. The other difference as well is that we have this line we have here is for 2D space. So we would need to have several more derivatives for our optimization. So yeah, these derivatives would be different. We'd have several more derivatives, and otherwise it's pretty extensible.
Mm-hmm. And one thing I'd like to point out, one of the benefits of TensorFlow even, so if you're talking about multiple dimensions, you can think of it as you have basically the same problem, and you're trying to minimize this loss function for a lot of lines. Technically, what's happening is you're looking at linear functions, since you're talking about, single output things. We're talking about, linear functions in higher dimensions. And so what you would do is instead of having one x value correspond to one y value, you have a matrix of one x values corresponding to their, relevant y values. And so basically you have this same problem, but instead of putting in one value and getting one value out, you put in a matrix of values and you get a matrix of values out. You're basically doing the same thing in higher dimensions. So you could be doing it for 300 different input values, and that's like a 300-dimensional problem. But obviously, you're not expected to think about it as a 300-dimensional problem. It's more that you organize the data such that you have a y equal to mx plus b as the first row of the matrix, or like an augmented matrix, and then the same thing for your second input, and so on and so forth. Just wanted to jump in and sort of point that out, so it's like doesn't become like insanely more complex. All right.
Yeah, that's a good way to explain it.
Does that answer your question?
Yeah.
All right. Wanna take that? Yeah, I think chat is lagging a little bit. We'll roll back around to it. So if that didn't answer your question, you can ask again.
Yeah. Kind of like Adi said, you have different lines with derivative, or each of those rows is their own mx plus b, but again, you have, instead of just x or whatever with weight, you've got one for respect for all of your inputs. Cool. Yeah, anyway, let's continue on. So yeah, we have our derivatives computed here. And then we need to update our m and b values depending on what those derivatives are. And also depending on our learning rate here. So this again loop is literally just what gradient descent is. We only have 15 iterations here, but yeah, that's the general idea. So if we want to actually see what this looks like, what the actual process of gradient descent looks like, this for all of them probably. Let's do it for the first 5. So this component just here is literally just to see the actual process of gradient descent from a graphical perspective, but all the computations being done here. And then I guess after that loop, we want to print out our values for our model. So this is, if we wanted to graph a line again to represent our data, that would be the slope, that'd be the y-intercept. So if you wanted to plug that into Desmos, for example, that's what you get. Oop, I think I have a typo somewhere. db. Oh, I forgot the yi. There we go. Cool. So yeah, we can scroll up to the top here. So this is our initial line because we initialized everything with 0. We've got the first iteration where we increase based on slope. The second iteration where we increase a little bit. Third iteration where we increase a little bit more. So as you can see, this is a fairly accurate line in terms of representing our data. And that's our regression done. As we can see here, those are our slope and our y-intercept values. So as you can see, it's pretty similar to just a y equals x line. We have a slight offset off there. We go slightly north of the x-axis, and we also are slightly bent towards the y-axis. But generally speaking, it's a pretty plain line. Cool. Yeah, so I guess that's the general gist accomplished. If we want to see further, we can compare. Yeah, I guess that against our overall model. Oops, there we go. That we've kind of ignored part of here. But again, this data is super simple. So 5 iterations gives you an extremely accurate model. So the extra 10 probably looks indistinguishable. Like even these two are fairly indistinguishable. Cool. So that's yeah, we're done now with the actual implementation. So if anyone has any questions about any facet of the implementation or gradient descent or anything, feel free to ask those.
Yep. We're basically at the end of the content that we have to present to you. These things can be, a little bit hard to wrap your head around the first time you do it, but I think Liam did a great job of explaining it. And so you can really see that it's basically fitting graphs to data, like Liam pointed out. But if you guys have any questions about what we did today, feel free to ask. Oh, we do actually have a question.
Yep.
Will we have access to the notebook after this?
Yes, I can make that public right now.
Sounds good. We can send the link to that in the Discord afterwards as well. So anybody who didn't attend or couldn't sit through the whole thing for whatever reason will be able to see the code. All right. Actually, we should be able to share the link right now, and then I will again share it on Discord. That's the link. It might not show up as a hyperlink on YouTube. YouTube's weird like that. Okay, do we have other questions? Right, we'll wait a few minutes, maybe 2 more minutes, see if there's any more questions. Otherwise, thank you for coming. Remember to please fill out the post-event survey. Be honest in your feedback. If you thought it was great, please tell us it was great. If you don't like, for example, YouTube as a platform, if you prefer us to do this over Zoom or something, please let us know. We can actually do that, but only if you give us your feedback and tell us that, hey, this is not working. With that said, I'm checking chat to see if there are any more questions, and it looks like there aren't. So thank you guys for coming. We'll hang around for just another minute to make sure there's no questions, and after that, we'll break away. So thank you guys for coming. And we hope you enjoyed.
Yeah, I guess just briefly, if there are no more immediate questions, we can go over kind of like an approximate what it would look like to have a third variable.
Yeah.
Baha, that's it's pretty straightforward. So again, our initial prediction line will depend on more things. So let's just have an example where, just because it's easier to write, where we don't have it depend on x at all. Or actually, I guess we do need it to depend on x. Or not x, rather. We have our prediction depend on, what was, I don't remember your example. We can say speed or whatever. Let's go, oops, that's the wrong way. So we have our change these up. 5, 2. So let's undo that. That's a little bad for fitting. I'm just gonna actually increase everything by either 1 or 2. Let's do it alternatively. So 5, 5, 6, 10, 11 there, 9, 10, 14, let's go 13 or 15 maybe. So let's just say whatever. This is your third variable. We have these two dependers, or actually we need an entirely new line formula, I guess. So we have yp depending on those. Yeah, because we've got basically y equals x plus z as our new line. We'd need a derivative with respect to c, which is more or less like this. Except we have, so that just gets zeroed out. It gets zeroed out. So actually, it looks more like the dm. Our chain rule is a bit different. We have z sub I. Z sub I z. Same update rule. Or we didn't initialize c, did we? And then we can't really see it. I guess we could still see it, but it wouldn't really be fruitful. Oh, I forgot to upload that again anyway. Is there error here? I forgot to zip that. So yeah, I guess our z values kind of threw things off. That sounds roughly right. I think there's some small error. Oh, it's okay. Part of it is also because we don't have a c value for the other line, I guess. But yeah, that's the general idea. You have another derivative with respect to the other variable, and you update your prediction based also on that. But yeah, general idea, hopefully there. Cool. I think we're basically out of time now.
Yeah, I think we're out of time, so I'm gonna go ahead and basically close out the stream. Thanks for coming. Thanks for asking questions. And we'll see you guys in the next workshop.